For this lecture, we're going to be discussing ionizing radiation hazard control. So for the previous lecture, we talked about just ionizing radiation basics, what ionizing radiation is, what some of the health problems it can cause are, as well as some sources of ionizing radiation. And in this lecture, we will be discussing how to control for those hazards. So there are three basic methods of control. These are just kind of traditional methods of control for external radiation sources. The first is time. So basically less time spent near the source means less radiation received. The second is distance. So obviously the greater distance you are from the source, the less radiation you receive. And the third is shielding, which is the concept of using a certain kind of material to block the radiation from reaching you. So this lecture is going to focus on what these methods are and how they help reduce the amount of ionizing radiation that an individual may be exposed to. So first we will discuss time as a control measure, which is essentially based on the idea that spending less time exposed to radiation decreases your exposure. It's important to note that the dose accumulates in a linear fashion. So if you have half as much exposure, you have half as much dose. In the same manner, risk increases linearly as well. So controlling time exposure is a reasonable way to control the hazard because it can be an inexpensive method of control and it often doesn't require special materials. So some examples of time as a control method can be found in medical imaging. So for example, using a more sensitive film or reducing redundant procedures in order to reduce the amount of time exposed. So really optimizing the protocol and making sure, if you have a patient who's going to be going through a lot of different x-rays or scans, that you are making sure that you're not having them go through more than what they really need to. For other kinds of occupational exposure, such as using radioactive isotopes in a research study, simply optimizing your protocol in a way that minimizes time with the radioactive materials can help. You can also utilize half-life as a control measure. So in the previous lecture, we discussed half-life a little bit. So half-life is the time required for the amount of radionuclides to reduce in half, meaning the activity level falls by half. The radioactivity level falls by half. If you can let the material decay to a safe level, then it's easier to deal with. So this assumes, of course, that you have time to deal with multiple half-lives. So for example, uranium-238 has a half-life of 4.5 billion years. Obviously, that would not be practical. You cannot wait for the half-life to pass because we don't have time for 4.5 billion years. But if you're working with something with a short half-life like bismuth-214, the half-life is close to 20 minutes, so that is a lot easier to deal with. So you can, if you're working with the material and you need it to be less radioactive, you can wait even a day, and a lot of half-lives will pass by that time, making it much safer to work with. So in this little figure here, this is just a visualization of how time relates to radiation intensity for the half-life. So for this imaginary substance, at the very beginning, you've got this representation of all of these little yellow particles are the radioactive particles, and after the first half-life, only half of those particles remain. Another half-life passes and you have a quarter of the original amount of activity. So to calculate half-life, or to calculate activity that remains after a half-life has passed, or after a certain amount of time has passed, you can use an equation that relates activity to initial activity and the time of half-life. So you can see a half-life equation here where NT is the quantity of radioactivity remaining. This can also be thought of as activity remaining. So this could be either thought of as the amount of material remaining or the amount of radioactivity remaining. And then N0 is the initial quantity, so it can be, again, either the initial amount of the substance or the initial amount of activity given off by the substance. Lowercase t is the elapsed time, and then t half is the half-life of the substance. So we're just going to go through kind of a brief example of how to use this equation. So like I mentioned in the previous slide, we can use this equation to measure the amount of material that is left, or we can also use it to measure the activity of the material that is left, so the radioactivity over time. So in that case, instead of using N to express the amount of material, you would use A as a representation of activity. So A is activity at the time of measurement. AI is the initial activity that you're starting with. Capital T is half-life, and lowercase t is the time elapsed. Both t's should be in the same units. So for example, if you have a half-life of 20 minutes and you're looking at how much activity is left after 2 hours, you would want to make sure that lowercase t is not 2 because your half-life is in minutes. So it would be 120 because it's 2 hours, 120 minutes. So for example, we have this hypothetical substance. It has a half-life of 3 days, and we're starting with activity of 10 millicuries. And we want to know how much activity will be left after 2 weeks. So again, you got to make sure that you have both t's in the same unit. So for 2 weeks, we would change that to 14 days. So we have 10 millicuries times half 14 over 3, and that would leave us with 0.39 millicuries of this activity of this substance after 2 weeks. We can also use distance as a control measure. So the further away you are from a radioactive source, the less your exposure will be. So for electromagnetic radiation, which again is gamma and X-rays, the inverse square law applies. This means that there will be an exponential decrease in intensity, so it gets less and less the further away you go, but it never goes quite to 0. However, for particulate radiation, such as alpha and beta particles, there is a defined range in the air. So the particles only go so far and then no further than that. This range is shorter for alpha radiation and longer for beta. Because alpha particles are highly charged and massive, they interact very strongly with air molecules, and then that makes them have a very short range. And then their range depends on the energy of the alpha particles. So for example, 1 MeV, or millions of electron volts of alpha particles, has a range of about ½ centimeter. But beta particles are lighter and faster, so their range is further. They also have less energy than alpha particles. So for example, 1 MeV of beta particles has a range of about 600 centimeters. So this is about 1,200 times as far. The range is about 1,200 times as far as alpha particles. The third category of control is shielding. So shielding is the process of using a certain material to block radioactivity from reaching the person. For shielding of gamma and X-rays, there's an exponential decrease in intensity as the radiation passes through some sort of material. The coefficient, or the attenuation coefficient, depends on both photon energy and material characteristics such as density and atomic number. So the amount of radiation that is shielded is going to depend both on the photon energy of the radiation as well as the material that is doing the shielding. So the pictures on this slide show some examples of shielding you may be familiar with, and perhaps you may be most familiar with the lead vests that are used during X-rays, which you can see in the bottom left picture. So these are vests that are lined with lead, which is a good shielding substance, and these vests help protect your organs from being exposed to X-ray radiation. The half value layer is a concept that is related to experimentally determined values of thickness of certain materials related to certain isotopes that reduce radiation of those isotopes by half. In other words, how thick does something need to be, does a specific kind of material need to be to reduce the activity of a certain radioactive isotope by half? So this concept is really helpful when trying to determine how much of a certain material you need to shield properly from whatever radioisotope that you're working with. So as shown in this table, if you're working with cesium-137, you need 0.65 centimeters of lead to shield in a way that reduces the activity of that radioisotope by half, while you need 1.6 centimeters of iron or 4.8 centimeters of concrete to achieve the same results. So you need, so lead would be the ideal thing. You wouldn't need as much of it. Whereas iron, you need a thicker shield, and concrete an even thicker shield. So this is a good way to conceptualize the idea that different materials are more efficient at shielding radioactivity than others. In general, it's easier to shield alpha and beta particles compared to gamma radiation or X-rays. So alpha particles interact, like I said, so strongly with whatever matter that they encounter that it makes it very easy to shield radiation from them. So for example, even just a layer of dead skin cells or a sheet of paper is thick enough to stop alpha particles. Beta particles are much more penetrating, but still not nearly as penetrating as gamma rays. So like shielding for gamma rays, the shielding of particulate radiation depends on the density or the makeup of the materials that you're using to shield with. Now that we've discussed how to control radiation exposure from an outside source, we also need to briefly discuss protection from internal sources. So it's possible to accidentally inhale or ingest radioactive materials, particularly in occupational settings. So there may be, for example, radioactive dust in the air as a byproduct of something that you're manufacturing, or maybe you have an accident in the workplace. So for example, when I was a grad student, I had a syringe that had radioactive material in it, and I accidentally stuck myself with the needle. Thankfully, it didn't get injected into me, but obviously that is a way that internal radioactivity exposure can occur. The best way to control for internal sources of radiation is, of course, to prevent intake. So just stop the internal source of radiation from even reaching the body. So ways to help achieve this are, for example, contamination removal from surfaces. So making sure that everything is clean and the radioactivity contamination on the surfaces is cleaned up regularly. Because you don't want to be having a surface that's contaminated and then maybe you touch it, somebody touches it and they don't have a glove, or they have gloves and then they touch their mouth or something and it gets into their body. Also, ventilation and filtration are very important. So actually, HEPA filters were first developed for this purpose, to filter out radioactive particles in the air. And then also doing respirable dust measurements and that sort of thing. We also have to consider both the radiation and biological half-lives when thinking of the effects on the inside of the body. So how long is that material going to stay in the body? It's not just the radioactive half-life, but the half-life of how long it's actually going to stay in the body. So by considering this, you can actually shorten the biological half-life by giving medications that can help remove whatever was ingested, and that can help kind of control for the amount of exposure that the person is receiving. The most important potential source of internal contamination is radon, which we covered in the first lecture, but now we're going to discuss how to control for radon exposure. So radon is often found in the bedrock or soil below buildings and can enter buildings quite readily. It can enter through things like construction joints, gaps around service pipes, cracks in the wall, gaps in the floor, sump pumps, and groundwater supply. Ventilation of radon is possible, but it's inefficient. So the best method of controlling radon is to prevent entry into the building, which you can probably see is just kind of a theme with control, is just to stop the hazard in the first place. So this controlling for radon and preventing it from entering the building involves sealing against entry of radon gas. If there's a significant pressure differential, you can fix this by a number of steps, including a gas permeable layer, plastic sheeting, sealing and caulking. Some of those, we talked about the gaps and things like that, sealing those up, using vent pipes and junction boxes. On the last two slides, we will discuss some other factors that are important for radiation safety, particularly in an occupational or medical setting. There are a number of administrative considerations that can be implemented in the workplace that can help reduce radiation exposure. So these are things such as institutional radiation safety programs, radiation safety committees, having radiation safety officers who monitor the use of radiation in the institution, state licensing and regulations, special training programs for users, and personal dosimetry programs. So research centers and hospitals should always have radiation safety programs and monitors in place to protect not only the employees but also the patients. These kinds of programs often involve things like monthly radiation monitoring of surfaces that come in contact with radioactive materials. So for example, doing swipe tests of different surfaces in a lab and using a Geiger counter or a scintillation counter for the swipes to see how much radioactivity is present on these surfaces. And that can give you an idea of if there's contamination that needs to be cleaned up. So doing this monthly is very helpful. And then having, special training of any users, like in-depth training of for users who use radioactive substances so that they understand the dangers and hazards and how to control for them. And also using wearable technology. So this is the personal dosimetry that I mentioned. So if you have workers who are radiation techs in a hospital, they can wear like little personal dosimetry badges that monitor their accumulated individual exposure. So finally, there are set rules that anyone working with radioisotopes should always follow for safety. So these rules include proper storage rules, which generally means having locked posted storage, or in other words, if you're working with radioactive materials in a lab, you want to make sure that you're storing those vials or whatever they are in a locked cabinet, and that your lab is locked, and that you have signage that indicates that there is radioactive material in that lab, and that it's locked up to prevent access by individuals who are not authorized to use radioactive materials. Also, there are special waste disposal procedures that are very important for occupational use of radioactive materials. Elements with short half-lives are typically allowed to be retained until they decay to a background level of radioactivity, but materials with longer half-lives require special disposal procedures. This can really vary, the procedures can vary by institution or workplace. But in this figure, in this graphic here, this is by the U.S. Nuclear Regulatory Commission. This shows a low-level radioactive waste disposal site. So this is a site that is specially designed and by this commission, and they accept radioactive waste from states that are participating in a regional disposal agreement. So this is specially designed to contain low-level radioactive waste in a way that is safe for the environment. And then finally, there are also special disposal procedures for radioactive material after it's been administered to either an animal in a research setting or to a patient. And again, these sorts of procedures can vary by institution.